levels just like the level of buckets of water, either in a bucket or a bucket connected to a swimming pool or an ocean. In this case, for a metal, you can put in a lot of water and not change the level of the water in the Pacific Ocean. And the same thing happens when you add or pull out electrons from a metal. Its capacity to accept and remove electrons per unit of energy is very large. But in a semiconductor, because there were no states here, if you pull a few charges out of that conduction band, the probability of finding an electron plummets rapidly. And so you don't have to move many charges out of this solid in order to move its Fermi level down. And so what happens in this case is the Fermi level of the metal hardly moves up, but the Fermi level of the semiconductor moves all the way down. Now, it doesn't matter if I had two doped solids, one would move up and one move down, they'd end up in the middle. It's just easier to see in this limit what happens. What happens as a result of this? This initially neutral solid, which had as many electrons as it had electron vacancies, it was neutral, is now no longer neutral. If I look at this under a microscope, I see the dividing line, and electrons have left this phase. This phase is now positively charged. And electrons have gone to this phase. This phase is now negatively charged. Right? There is now an electric field-based asymmetry in this entire device, because this phase is positively charged, this phase is negatively charged. Now, what will happen is it's not going to stay this way, because these positive charges want to snuggle up next to the negative charges so that their positive and negative attraction is maximized, and that happens when the distance is the smallest between opposite charge carriers. So all the negatives on the surface of the metal, because metals don't support electric fields, go to the surface of the metal. All the positives try to get as close as they can to the surface of the semiconductor, but they can't all sit on the surface because they reside on the places these electrons left. They were plucked off of those phosphorus atoms. And if we don't put many of them in the lattice, we have to reach further in to get all the phosphorus atoms plucked off with electrons. Okay? This distance, therefore, is controllable by how much we dope this. And instead of being one atom, like a metal, can be on the order of a tenth of a micron. Right? That's really good. Because what happens then is, if you pulled out electrons for on the order of a tenth of a micron, then it's easy to show that if you have this charge density